Okay, thanks, Andy. So the DART mission is fast approaching, launch in 2021, and impact will be in 2022. And in preparation for this mission, we've been doing a lot of hydrodynamic simulations of the impact, specifically using the spheral hydrocode, which we'll be talking about today in this talk and several other talks later on as well. But interpretation of the detected nudge velocity that we'll see from that mission will depend on a variety of initial conditions, some of which are constrained and some of which are unconstrained, or at least they're unconstrained right now. They might be constrained after DART and the HERA missions occur. In the constrained category, we of course have the spacecraft mass, 555 kilograms, the velocity, 6.65 kilometers per second. That's the most recent estimates from the engineering team. And another category, and another aspect that's not been discussed too much, and we're starting to get more into the details here, is the impacting spacecraft shape. And Mike Owen will be talking more about that today, modeling the entirety of that shape model, including these solar panels, and seeing how that affects the evolution of the crater. In the unconstrained category, we have the target's rubble pile distribution of boulders, and that's going to be discussed in detail in Don Graninger's talk later today. We know that asteroids have rubble pile structures, and the details of where the impact occurs are going to matter probably. Whether it's near a boulder or on a boulder, it's going to change the outcome. The impact angle, and that's the focus of my talk today. I'll be looking at, in a systematic way, at how impact angle affects the asteroid's response to the impact. And this is going to depend on a couple of different things, both the broader shape of the asteroid, the Didymos B shape, and as well as the impact site geometry. And finally, target material properties like strength, porosity, and composition are going to all matter, and I'll talk a little bit about those as well. We use Spheral, which is an adaptive SPH code. It's open source. All of the simulations you see today will be in 3 dimensions, because for these types of problems, we feel like you really need 3 dimensions to fully understand what's going on. Spheral is a meshless code, which is really wonderful for tracking ejecta accurately, which is what we need for the DART simulations. It's very extensively benchmarked against geological experiments. Don Graninger and Tane Remington specifically have spent a lot of time recently comparing to experiments using geological materials like granite, basalt, and ice. So we have a lot of confidence in how it's going to work in situations like the DART impact. So to begin with, looking at composition, the figure of merit in a lot of impact simulations when you're trying to deflect an asteroid is beta, which is a measure of the enhancement that you get from crater ejecta. And so what we're looking at a lot of times in these studies is how beta varies with different initial conditions. So this is from a previous DART workshop, some work looking at how composition affects beta. And we found that for available equations of state for geological materials like granite, basalt, and pumice, it was not particularly sensitive to composition. Beta varies on the order of a few percent, but it's not a huge lever on the final result. And I should mention that at this point, when we were doing these simulations a couple of years ago, we were modeling just near the impact point. As you can see there, it's like a little ice cream scoop about 20 meters in radius from the impact point. Since then, we've decided that it's necessary to model the entirety of Didymos B. And so all the simulations you see from our team today will be showing the entire ellipsoid of Didymos B. Another material property that we think about with asteroid impacts is porosity. Most asteroids are underdense, and so porosity is either in the form of microporosity or macroporosity or some combination. Porosity eats up energy. More energy is partitioned into heating and less is into ejecta. And so that lowers beta to some degree. But what's interesting, what we found a couple years ago, is that for an asteroid of a given volume but unknown bulk density, if the porosity is higher, yes, your beta will be lower, but the total mass of the asteroid will also be smaller. And so the delta V, which is the measurable quantity in the experiment, will actually be higher. And so we found that in this case a couple of years ago. The craters produced in porous impacts, of course, are going to be deeper and narrower. The impactor penetrates more deeply, and the shape of the crater becomes more elongated. Strength is another material property that's important for determining beta. One way to get at asteroid strength, we have no direct measures of asteroid strength, but one way to get at it is to look at meteorites here on Earth and do experiments on them. Desiree Cotto-Figueroa looked at a variety of meteorites recently and found that chondrites become weaker at larger scales more rapidly than terrestrial rocks, which has implications for how we model it. And so for a reasonable range of cohesion values in our simulations, we found that beta varied on the order of 10% or so, but it wasn't a huge lever on the final delivered momentum push. So strength's going to matter, but for the more likely range of strengths, which is probably somewhere between 1 kilopascal and tens of megapascals, it does not vary too much. The shape of the Didymos moon is still uncertain. It's a couple pixels or so in the radar images, and from light curve data, there's some estimates of the elongation of the object. We really don't know what the shape could be. So it's important to be prepared for a variety of shapes. Here I'm showing some work from a study we did a couple years ago with Dan Shears and Jules Feldhacker, where we used the asteroid Glevka as a test bed for looking at shape effects on the delivered momentum to asteroids. So we made a comparison between spheral calculations and an analytic model for how we would expect beta to vary with impact angle, and found that they were broadly consistent as long as the angles were not too oblique. But as you got to more oblique angles, things deviate a little bit more between the analytic approximation and the numerical simulations. And later today, Tane Remington will consider an even weirder shape than Glevka. Glevka's interesting, but she's going to be looking at a scaled down version of comet Churyumov-Gerasimenko, which is very bilobate, and it's an interesting test case to look at shape effects. The focus of my work today, all the new stuff I'll be presenting today, is looking at a systematic study of how impact angle affects asteroid response to a kinetic impact mission. And for this, we're modeling the entirety of the Didymos B target. It's represented as an ellipsoid. Its elongation is currently estimated from light curve data, which are, you can see that listed in the Didymos reference model. And what we're doing here is we're having very high resolution at the impact point on the order of 5 centimeters. In terms of mass, about 75 grams per particle. And then it's ratioed out as you go to the back of the asteroid. So depending where the impact point is, you can see how in those colors there on the screen, how the masses change. The red is the very massive particles, and blue is the small, finely resolved particles near the impact. So in each of these simulations, there's about 8.5 million ASPH particles. Here we've assumed the porosity of Didymos B is 30%. That equates to a density of 1.9 grams per cc or so. We're using Grady-Kip tensor damage. This is all using a granite US and granite Weibel parameters for the damage model. The way we've conducted this study is to keep the x velocity constant, so it's coming in along in the x direction there at 6.65 kilometers per second, but then we're just moving it in the z direction upward, so it's more and more offset from the axis of symmetry. You can see how the impact angle changes there as it goes from 20% off axis to 50% off axis to 80% off axis, moving from 72 to 48, 26-degree impact angles. We're moving in the least forgiving direction of error, which is the semi-major axis is 66 meters. So we don't know the shape, so even small targeting errors could potentially lead to a large impact angle. So we're interested in testing that. And here, what this does effectively is it splits the ejecta momentum into x and z components. And in real life, if it were offset in three dimensions, it'd be further split into 3 components. So here's 4 different impact angles. Looking in cross section, you can see the 90 degree, 72 degree, 48 degree, and 26 degree cases. Looking at the damage on the top, red corresponds to fully damaged material. Gray is not damaged at all. So damage extends roughly 13 to 20 meters from the impact site. And on the bottom, you can see all of the velocities of ejecta particles in the x direction. So that's material that's pushing in the preferred direction, the direction of that we're trying to push the asteroid in. The approximate escape velocity is 5 centimeters per second. So we've shown everything that's 5 centimeters per second or larger. Some of the fastest moving material is about 1 kilometer per second. That's in red. Some of that's outside the frame here. And at the low end, you're seeing blue material pushing at 5 centimeters per second. Notice that there's also some gray material in the ejecta curtain, which is pushing in the wrong direction effectively. So as you get to more oblique impact angles, especially the 48 and the 26 degree cases, you're getting some of that ejecta pushing in a non-ideal way. And the ejecta curtain morphology has become more and more asymmetric. More momentum is going into the downrange component of the ejecta curtain as you get to these oblique impacts. And just zooming in on one of the cases here, you can see all of that gray material in the downrange direction. That's all pushing in the wrong direction for beta. That's going to directly subtract from the beta that we are calculating. Another interesting thing to look at is the time evolution of beta, especially for these very oblique cases, the 33 and 26 degree ones, and magenta and cyan here. You can see that you can see that beta dips below 1 at these early times because it is so asymmetric, and there's a lot of momentum in the downrange component that's pushing in that wrong direction. And eventually, over time, these betas get a little bit above 1, but at early times it's so asymmetric that it's less than 1. Let's see, here's a movie. Hopefully it works. Okay, yeah, this is just a movie of the 48 degree case to give a sense of how asymmetric the ejecta curtain is. All of that gray material is pushing in a non-ideal way against the direction we want to push. Okay. So here we're plotting the analytic prediction we would make based on sine theta squared scaling for these different impact angles. That's in blue versus the numerical results, which is in black. And you see that at pretty close to normal impacts at 60 degrees and above, they agree pretty well. But as you get to more and more oblique cases, they deviate from each other, and beta drops off at a faster rate for the numerical simulations in spheral, which makes sense because the ejecta curtain is not going to stay symmetric as you get to these very oblique cases. And here we're just showing the same results in a table. The delta V's that these betas correspond to are somewhere between 0.8 and 1.4 millimeters per second. And now an interesting development within the last few weeks has been the successful fielding of the Hayabusa 2 SCI impact experiment. And I think this really shows the importance of 3D modeling for asteroid impacts. And I'm not on the team, so I don't know any of the details beyond what's on Twitter and so forth, but you can see that this ejecta curtain does not look axisymmetric, at least the way it's viewed here. And so that whether that's being controlled by the impact angle or local topography, it really calls attention to needing to use 3D models to capture the realistic development of ejecta and these types of impact experiments. And so I'm a little short on time, so I'm just going to leave the summary slide up and take questions. Thank you.
Before you actually engage the asteroid, how is it that you actually determine an aim point on the asteroid? How do you determine where you're going to actually?
Oh, so we start with the center of figure. Is that what you're
Yeah, the
stating?
spacecraft autonomously targets the center of figure. You don't. It's the center of figure. You target the center of the image that you see.